he has another talk tomorrow, or he's going to tell us about something else, but they're going to be connected, right?
Right.
So
yeah.
Please pay attention. Thank you very much.
Okay, yeah, so let me first thank Umut for putting this conference together. I think it's a great occasion to have, to try to understand each other, like the algebraic geometric approach to mirror symmetry and mirror constructions, and partly still ongoing, and constructions of mirrors in symplectic geometry. In my mind, it's very closely related. And the reason that some people think it's something pretty much different is has more to do with the fact that on the surface it looks very different what we are doing. Okay, so in preparing this talk, I specifically had Umut in mind because I also didn't know who else would be here. So I'm trying to, it will be a technical talk, okay? So, but I'll try to go very gently, and the aim is to explain these strange invariants that I defined together with Dan Abramovich, Chile Chen, and Mark Gross over a period of almost 10 years, from 2011 to, we struggled with the topic, and it was finally finished in 2020. To have these weird invariants that have kind of negative contact orders. And in doing so, I am forced to not sweep under the carpet the technicalities. So either one talks about it in a very general terms, and then that's fine. But if you really want to tell something a little more interesting, you are forced to talk about log structures at some level. So let me start with a gentle introduction, hopefully gentle introduction into log structures, and then we'll get to the, hopefully at the end of the talk, to really get to the nitty-gritty, the key points in punctured invariants and how they differ of logarithmic grammar-fitting invariants. And then in the follow-up talk, I will show, hopefully be able to explain how these invariants are at the center of understanding wall structures that Mark and I had in our mirror construction for, well, from, what was it, 2007, which at the beginning was a combinatorial gadget, combinatorial algebraic geometric gadget, and give it an enumerative interpretation, which essentially tells you how to alternatively get these structures from the symplectic point of view. Okay, so let me start with log structures, and please, if you feel like, okay, this is over your head, interrupt me. It's really, this talk is for you, right? It's I want to make sure that everybody can get something out of the talk.
And I also want to make sure everybody can hear you well. Yes?
Is the audio okay?
And see everything. Okay, so the room has corners that you don't see, and that's where the people are congregated for some reason.
But I can maybe make it a little louder, but I can hear you clearly.
We can increase the volume.
No, I'm fine. It will be too loud. It's okay. I hear you very clearly. Okay.
Okay, perfect.
Okay, so let's start with log structures. So I think the easiest way to motivate log structures is to look at this normal crossings, at a normal crossing situation. So X would be smooth. D is a divisor of with normal crossings with several components. Let's say DI is given, I write it globally, but it could be a local equation, V of ZI. And to be even more concrete, let's think of A2 with the two coordinate axes. And then whenever you take a K tuple of natural numbers, you get an effective divisor, some AIDI. And an associated ideal sheaf or line bundle OX minus some AIDI. So these are the functions with zeros of order at most AI along DI. They're generated by these functions. Okay. So what I want to do now is I want to pack this, or what log geometry does is, I want to talk about these kind of line bundles simultaneously for all A's. And you can do this easily by looking at regular functions that have zeros only on D, at most on D, okay? So they're invertible away from D. And of course, that's not a coherent sheaf, but it's closed under multiplication and it has a unit. So it's a monoid sheaf. The stocks are given by an invertible function times some monomial in the Z1 to ZK. Okay, so this is what this weird object looks like. And essentially, all the log structures locally look like that we are interested in kind of look like this locally. Except we will kind of have more abstract monoid sheaves that only kind of are obtained by restriction of these things, but I'll get to that. So then obviously you have an order of zero function that just records these powers A1 to AK, right? So that's a morphism from MXD, morphism of monoid sheaves, to this direct sum of sheaves supported on the DIs. Okay, so this has kind of rank L when L components of D meet, and generically it's just zero. So if you're away from D, it's a zero sheaf. So that's really the quotient f of mx comma d by the invertible functions. You just forget about these factors, you end up with the powers. And that's always denoted m bar. Okay, so the m bar log geometry has discrete parts. It's totally captured by the m bar. And we will learn that the same information can be recorded tropically. Okay, so this is where tropical geometry kind of will happen. And then there's some part that has to do with line bundles that come from this map kappa. Let me try to explain this very concretely. So whenever you have an open set U and X, and you fix a tuple, that should be a K, not an R. Oops. And a K tuple of natural numbers. So I've used it as a section of this M bar sheaf over U. Then you can use the pre-image of this M bar under kappa, and you will get an OU cross torsor, right? You can kind of freely vary this H. And when you see the associated line bundle, so you turn the torsor into a line bundle by doing this thing here, is just OX minus some AIDI. So in this sense, we have now successfully packed all these line bundles having to do with these effective or minus effective divisors into one gadget. Okay, so and then you get this exact sequence that you might want to look at. This is really an exact sequence of Boolean sheaves. I go over to the group, the corresponding Grothendieck group. So this would just would be the direct sum of Z DI. You replace the N by a Z. And then you have kind of sheaf you may not want to think about at the moment. Okay, so this can take negative powers over here. And that is the point of view. So this kind of, there's a functor hidden, right? So you take open subsets and you have some sheaf M bar, and then you have a functor from these sections to line bundled or OUSR torsors. And that is the point of view taken by Deligne-Faltings on log geometry. I will take a slightly different point of view, but it's useful to think about it, especially because Tirani, in his version of, in his theory, in his attempt to generalize logarithmic Gromov-Witten theory to symplectic geometry, uses exactly this point of view. So he's restricting to the normal crossings case, and he has kind of these vanishing orders A1 to AK, and he looks at all these line bundles and various rules and how to multiply them. Yeah. So observe, this whole thing is still multiplicative, right? So the line bundles alone are not enough. You also have to know how to form tensor products and how you multiply sections with different vanishing orders. Okay? Are there questions on this first slide, or is this all trivial to everybody, hopefully?
I didn't understand the exact sequence. Why did we talk about that? What was the...
No specific reason, to be honest, but it might be more kind of obvious to some people that if you write it as a sheaf, as a set of sheaves, how to get the line bundle, right? There's a connecting homomorphism from sheaves sections here to H1O star, and that's the Picard group, right? So this will be the line bundle, actually.
So, but you mentioned something about changing N with Z, and when you were talking about this?
This is just a group, right? So this is a sheaf of monoids. You cannot invert, right? So adding the inverting the elements, or this one, right? Rather, this is the M bar. That was my M bar X comma D. So if I take a group here, that would just change the N to a Z.
Okay.
Okay. Thanks. Okay. So of course that's, I mean, if you are just interested in pairs X comma D, you would never need to do anything abstract. You just work with a pair, okay, and functions like this. But of course, that's not the point. The point of log geometry is that there's a whole category, and you can pull back and these kind of things. So how do we get interesting log structures starting from Mx comma D? So one fundamental construction is if you pull back log structures, or you restrict also. The restricting is, of course, a special case. So let's say we have a morphism f y to x, and we have x is still our x from before, so we have a divisor. And then you can form the log structure that's typically written f upper star mx comma d. You pull back the sheaf as a sheaf, and then you take the fibered co-product, adjusting the invertible functions. So what's wrong with this thing, right? This doesn't have, that guy here doesn't have a morphism to functions. It would go to f inverse ox, which is not oy. So you force this by doing this fibered sum. So this is this diagram, right? So f inverse ox star is a subsheaf in here, and it's also a subsheaf in here. And this f upper star mx comma d is then the fibered sum of the two. So maybe let's not think too much about it at the moment. It will definitely be something that still has a map to some m bar. So f upper star mx comma d still maps to f inverse m bar x comma d, and the construction is compatible with the line bundles. So the line bundle that you get for f upper star m bar will be f upper star of the line bundle you get for m bar. But this construction gives you two very important constructions. So let me go to the first one. So first, as normal crossings, just to kind of, for psychological reasons, that construction obviously works for any divisor, right? You can just write this down. It's just not as concrete, right? This wouldn't be correct. It can be a mess. But another case where it works very beautifully is toric varieties. So let's say we take the affine toric variety, spec C of Q. So Q would be a submonoid, finitely generated, saturated submonoid of some Z to R. And I assume that I have, just for being specific, a zero-dimensional stratum, a unique zero-dimensional stratum. Okay, so that means that Q has no invertibles other than 0. Let me call this point P. So something like A2 in the origin. Then Q would be n squared. And doing this construction here, the f upper star mx comma d, so going over to Yoda upper star mx comma d, where d is the toric divisor, produces what is called a lock point. So this is a point, it's a scheme, spec C, but it has an interesting log structure. So, and that's written as spec Q to C. So the Q to C is a standard notation in log geometry to tell you how to put an interesting log structure on C. When you write this, what you typically mean is that you take an element of Q, you map it to 1 only if Q is 0, and to 0 if Q is not 0. This looks a little weird, but how does this come about? Well, each Q, let me maybe write this down, each q really gives you a function. Let me call it z of q, okay? And what I wrote down, this thing here, this is actually nothing but z to q restricted to this point p, evaluated p. Oh gosh, here. Yeah, so it's 0 for any non-trivial monomial, and it gets 1 only for the trivial monomial z to 0. That's how this comes about. So these are log points, and the most important case, of course, is a standard log point where a q is n. So this means you take this is a 1 parameter case. There's only one interesting. Well, there are 2 interesting, but this is maybe one interesting. One-dimensional toric variety, which is A1, affine toric variety apart from GM. And that's what you would get, the standard log point. And why is it important? It will come up over and over because this is really the 1 parameter case. So whenever you talk about 1 parameter situations, you work over the standard log point. Okay, so it typically comes up in stable reduction situations, for example. But I'm jumping ahead. I'll explain a little more when we talk about the degeneration situation. So let's assume we have, let's say, a semi-stable degeneration. So meaning X is smooth over the spectrum of a discrete valuation algebra, complex algebra. And so then the central fiber is a normal crossings divisor, and we can look at the log structure of M of X comma X0. And that endows, and then I pull back by Yoda, and that endows the central fiber X0 with a log structure. This is this guy, okay? And the miracle of log geometry is that the log structure contains just enough information of this degeneration, or it keeps enough information of the degeneration to be useful. So for example, this is enough to tell you in reasonable, under kind of reasonable assumptions, pretty general, the Hodge theory of that, or the limiting mixed Hodge structure of this situation, that you can read off from this. X0 alone wouldn't be enough. But what you see from this, I mean, this construction that I gave you with this pullback and so on is pretty obviously functorial. So it's not only a log space, but it comes with a morphism to the corresponding log space you get for this pair, which is the standard log point. Okay, so that the central fiber of a normal crossings degeneration is a log space over the standard log point. If you go to higher dimensional basis, that works too. So you could take S, a toric variety, but then you have to not just take the central fiber because you want it to be a divisor, right? You want X0 to stay a divisor. So what you do is you take the pre-image of the toric boundary divisor, let me call it XD, and then you get a log space XD, comma X, XD, you log structure, you pull back to XD, and that gives the log space over this log point that I had before. This is how more interesting log points come about, and spaces over more interesting log points. So log spaces over log points with higher rank monoids, they capture the limiting situations of higher dimensional families. Maybe let me pause here because
yes, I have a stupid question. So the image of this iota is the generic point or something, right? It's not.
No, it's a closed point.
It's the core. No, but up, like in the example above, is it also the closed point? So yeah.
This is zero bottom. So let's say A2 with the origin. P could be the origin A2. And then Q would be n squared.
An example. How did you said that you have to change X0 to XD?
Oh yeah. Yeah, good point. Yeah, so let's say we have right. So let's assume we have a family x over a2? That was your question, right?
Yes.
Is that your?
Yes.
And then you look in here, it's a d, which is a v of, what was my notation? I think z1, z2. Okay, and that is your xd. Okay, yes. And then, oh, but sorry, you are making a good point. I still want the origin, sorry. I said something slightly misleading. I still need this guy, right? I want the log space. What I really want is the following. I take, still call this Yoda. And what I want is the x0, and then I take Yoda upper star, but to define the log structure, I take the xd.
Oh, I see.
That makes more sense, right?
Yes.
Yeah, sorry, that was misleading. Any other questions? This particular example, it will not occur in this situation, okay? The situation where this occurs, that you have certain restrictions of log structures, that has to do with cases where this is a modelized space, typically. But actually, no, and in the mirror construction, that also occurs, yeah. Okay, let's continue maybe. But feel free to ask questions on this throughout. Okay, so now I think we are mentally ready to talk about abstract log structures. So what is the essence of this? I take a sheaf of monoids, MX, commutative monoids, and a morphism of sheaves of monoids to the structure sheaf where I forget the additive structure. So I just keep the multiplication. So when writing this, I write it multiplicatively. So that's maybe, I should pronounce this at some point, right? So in working with MX, I work multiplicatively as I do in OX, just thinking of the previous example where I had a log structure and I had functions, okay? But once I go to M bar, I think of the exponents and I will write it additively, okay? So M bar always additively, M and OX multiplicatively. Okay, so second condition, I want that the pre-image of the invertible functions maps isomorphically to the invertible functions. Okay, so we had this definitely before. The only invertible functions mapping to invertible functions are just the H, right? All the A1 to AK have to be 0. So this is a copy of O star. It's trivial here. But we take this as an additional, as an extra condition in abstract log structures. And then the third condition is typically not included as part of a log structure. And there are log structures that are not of this form that are interesting. For example, the ones, or notably the ones that you get for to define these Kato-Nakayama spaces or Betti realizations that might or might not have come up previously. Anyway, ignored here. Our log structures will always be the form F upper star of a log structure on a toric variety, locally. Okay, so locally, I want, that would be my X now, to map it to some affine toric variety. So I should write locally, right? So maybe a U inside X. This is typically called fine saturated log structure. Okay, I will not mention it.
Can I ask a question?
Yep.
Is this theory related with fields with one element in F1?
And which one?
You are introducing those sheaves of monoids and so on.
No, it has nothing to do with F1. No. Oh, is there proof?
Because you see, I mean, Toen, I think, constructs schemes over F1 using monoids.
To be totally honest, I mean, there are so many interpretations of what F1 is. I'm not entirely sure. There might be a framework where what you're saying is true. Okay. So I guess there is a category of, what did I call this? I don't know, F1 object or whatever, and maybe that's sheaves of monoids and stuff. It's possible, yeah. Okay, I'm not thinking of it this way, and I'm sure it's not useful for the talk. It might be useful for some reinterpretations, but not for this talk. Okay, so then we always have this M bar that we obtain by dividing out the MX model OX star, and from this condition, it follows that it's a finitely generated monoid. So something like a it's a sheaf of finitely generated monoids, something like the integral points of a cone in Rn. And I think of this M bar X as the kind of virtual vanishing orders along Cartier divisors of these sections of MX. And we have these OX star torsors for any local section of this M bar sheaf that I view as something like virtual, well, co-normal bundles. Something like OX minus some AIDI restricted to D. Maybe. Actually, why do I want to restrict to D? No, maybe not D. Let's remove it. Umut, that's a complaint?
I can ask that.
Okay. Okay, so let's go to one of the most fundamental cases for Gromov-Witten theory, log Gromov-Witten theory and punctured Gromov-Witten theory. This nodal curves. So let's say we have a nodal curve with L nodes, and to be specific, let's take a chain of 3 copies of P1, let's say. So then L is 2. And then there is for any nodal curve, you have a versal deformation space, which is a smooth base space and a smooth total space. So this thing here is, of course, a semi-stable family. This is a semi-stable family. And the whole thing fits together. This versal deformation of a nodal curve gives you a chart for around that point in a modelized stack of nodal curves. So there's a nice algebraic modelized stack of nodal curves. It's only an Ardian stack, but other than it's a very nice stack. And you have a universal curve over it. So this is this picture. So ignoring that it is a stack, or just looking at this thing, that it fits into the situation we had previously, right? Now we have a higher dimensional base, just as here. Yeah. And it induces a log structure on C0 over a base, a logarithmic point, N to L. Yeah, so it's written here. So we get a log structure on this nodal curve without doing anything. It's canonical over the spectrum of, well, these kind of logarithmic point with monoid N to L. And the N to L, of course, has to do with these smoothing parameters of the nodes, because these will be the divisors. Well, I didn't say this. I hope you would immediately recognize it, maybe. So maybe I should write it. So the U, of course, has a divisor. Let me call it, should I call it D? Maybe U sing or something like this. Or yeah, maybe U sing or something, which is a locus of singular curves. And that's the normal crossings divisor inside the versal deformation. And this N to L comes, so of course, this is I can write it explicitly, right? This is the V of T1 to, sorry, too much dirt here. T1 to TL. So that is characterized by the vanishing of one of the smoothing parameters of the nodes. Maybe the benefit of being explicit, let me write down this log structure here explicitly, okay? So the monoid sheaf, of course, has only one stalk. So stalk is a C cross direct sum N to L. It has a structure map to C, yeah? So remember, we needed this alpha morphism here. This is the alpha morphism. And it maps alpha comma K to alpha times T to K, multi-index notation, at the origin, which, similarly to the log point we had before, is alpha only if K is 0, and otherwise it's 0. Okay, so this is explicitly this log point, and that's where the nodal curve lives over. This is sometimes called the basic log structure of the curve. And we will have a similar basic log structure for log Gromov-Witten theory and for punctured Gromov-Witten theory. And it's a very fundamental concept in log moduli theory. I might get to that, comment on this later on. Okay, so what is basic, or sometimes people also say minimal? And the minimality is, or basicness is reflected by the fact that it's a universal log structure, which means that any other, some loggy terms to be correct, log smooth integral log structure on a family of nodal curves arises by unique pullback from this log structure. Well, I shouldn't write C0, MC0. I wrote family of nodal curves. Maybe I make it correct on C0, okay? But it also holds in families, okay? Okay, so what does this mean? Let's now pull back to a standard log point. Okay, I told you that standard log points reflect a 1-parameter degeneration situation. So first, I can of course look at, let's go back all the way to the beginning, to A2, and look at some curve oscillating here to the origin, right? So something like T maps to, well, that's the wrong picture. I have a minus here somewhere. Let's say T squared T cubed. Yeah, that's the wrong way around. Okay. Anyway, T cubed T squared. So you can pull back the log structure by the thing. What would we obtain? So where am I? Here. So this is a morphism from this log point, the standard log point, to the thick log point with this bigger monoid. Of course, the arrows for monoids go the other direction, the other way. So that's a morphism from C cross direct sub n to L to C cross direct sub n. But there's no choice on the C cross because we want this to be an isomorphism on invertible elements under the alpha morphism. Okay, so what this really captures is a morphism from n to L to C cross direct sum n. And now you can see you have two components of this map. The one is purely discrete. It tells you the kind of osculation order of your 1-parameter family to the various divisors. So that was the 2, 3 we had before. Yeah, so written here. But then you also have another thing, which is the map from n to L to C cross. And this captures these coefficients, lambda 1, lambda 2. So within these families of log structures that you obtain by pullback, of course, you could introduce some factors here somewhere, right? You can write here lambda T squared, and then you would kind of get a whole family of such curves, all of the same shape, but of different, slightly different, yeah, I'm not sure how to say this, different rates. Okay, I call this the speed of this smoothing for a given rate. Let's try to understand this for this nodal curve. Okay, so we have the two nodal curve we had before. Then logarithmically, you have something you can write inside MC0, an equation Z1W1 is lambda 1 T squared. So typically, for the universal log structure, you would write Z1W1 is T1, and at the other node, Z2W2 is T2. And then restricting to one of those, base changing to a standard log point, you would replace the T1 by lambda 1 T squared and T2 by lambda 2 T cubed. But don't take it too literally, okay? I'm saving on notation here. T as a function, of course, is 0 on C0, but inside MC0, it's a non-zero element, right? It gives some, there's no 0 here anyway, right? It's a non-trivial element. So these equations do make sense in the log structure on C0, while they're totally trivial as ordinary algebraic functions. So that's the upshot, right? So the log structure on a nodal curve, let's say over a standard log point, or universally, if you work over a bigger dimensional space, they record the rates of smoothing of the various nodes, of the L nodes, and the speeds for these rates. So, yeah, so once, because you have this T, right? So you T downstairs tell you how you compare the speed here with the speed of smoothing here. Okay? Does this somehow make sense?
So, do we have a log structure on the space with parameter T, or?
I'm talking about two setups. So I tried to tell you before that this guy here has a universal log structure.
Yes.
So this is this nodal curve together with a log structure that lives over the log point with monoid n squared, or C star direct sum n squared. And then I do a base change to a standard log point, and now it becomes a nodal curve together with a log structure that lives over the standard log point. And that's what I wrote down here. Okay, so by what I wrote here, that defines the log structure over the standard log point on this nodal curve. And you should think of this.
We could map anything in, right? Any map from A1 to A2.
Not any. It should not map onto one of the coordinate axes, because that would mean yeah, that wouldn't induce a log structure, because then you have functions. Let me see. There is no, yeah. Maybe, yeah. Let's skip this discussion. Maybe it's too technical, but any that kind of enters to do this log point construction, you need a log structure that generically is trivial, right? So if you go to a coordinate axis, you can do something different, but it wouldn't work the way I stated it.
Okay. It's just 2 and 3 is just how quickly are you smoothing the nodes?
Yeah. And there's some discrete part, right? That's the exponents, and then there's some part that is in C star, and you can compare. Yeah. So let's say both coefficients are exponents are 1. Then you still have a relative rate of smoothing of the nodes. Yeah, so one goes like twice or whatever. Once you fix the Z1, W1, Z2, W2, but that's a choice once and for all. Yeah. Shall we?
There is a pullback nodal degeneration, and they're kind of computing the corresponding log structure by pulling back the log structure.
Yes. And that will keep this kind of relative rate of smoothing.
Okay.
Yeah. Okay, so then let me quickly, because we'll need that, tell you how to incorporate marked points, because that goes totally seamlessly. A marked point, as you know from the theory of stable or pre-stable curves, is a horizontal divisor, or just a divisor at a point on C0, but if you have a family, it will be a horizontal divisor. So this fits into a diagram of stacks, will be a closed substack of it's a divisor in this universal curve. And we can still do the same construction, except you add the Z to your what was it before, the XD or whatever I wrote, where is it? Over here, right? So there was the XD, which now is the CD. You would have to add the Z as another divisor horizontally. And the effect is that this M bar, which is a general point or generic point of a curve, so not a node, but any other point, before was just a copy of the base monoid. At these marked points, so this is, it adds another N factor that records the order of vanishing along Z. So the log structure at this point looks as maps Q, K to alpha of Q, that comes from the base, and times Z to K, where Z is the local equation of your marked point. of the capital Z. Okay, so it just acts these n factors horizontally. Okay, so if we are basically fine with this level of log geometry, one of the aspect of the whole story, most gratifying thing probably, is that there's this underlying tropical geometry, and tropical geometry arises very naturally in this setup. So how does this go? Well, obviously, I mean, if you know about tropical geometry, you know it has to do with degenerations, and this is also another language of dealing with degeneration. So at some point, tropical geometry should come up. So here's how it goes. So start with any log space. It's totally general. And I will have two running examples. One is P2 with its toric boundary. And the other one is this two nodal curves that we had before, but I add one mark point to make it a little more interesting. So I have two nodes, Q1, Q2, and the mark point P. And I view this as a curve with its log curve, with its basic log structure, so with monoid and squared.
Sorry, so mark point changed the log structure. Is that what happened? Is that how?
Yeah, it changes the log structure on the universal curve, not on the base. Yeah, it just adds these factors of n along the mark point. Or
okay.
sectional, whatever you want to call it. So then,
also, but why is it n cubed here then?
Say it again.
Why isn't it over n cubed? Why isn't it over spec n cubed? See?
The P does not change the base monoid. Yeah, so these factors have to do with these equations that you get Z times W equals T at a node. Here you don't have an equation that has to do with the base. It's purely on the fibers. Yeah, think of the moduli space of stable curves. The boundary divisors have to do with smoothing of the nodes, not with moving the marked points. The marked points don't really change that structure. It has only to do with the nodal structure. Okay. So the construction is whenever you have an X, schematic or close point, you get a finitely generated model at this MX bar. Well, we assume they are all FS, fine saturated log spaces. So then this will be a finitely generated monoid. You can dualize this by dualize in the following sense, namely you take the homomorphisms as monoids from MX bar to R larger equals 0 with the multiplicative monoid. Wrong. Additive monoid, damn it. Maybe I should write it here. Okay, so I call this M bar X dual, slightly inconsistent with notation in our papers. Anyways, so that's a rational polyhedral cone. It's not discrete anymore. It's really an honest cone. And then the next observation is that if you have the generalization induces phase inclusions of these cones. So how does this go about? So let's say X is in the closure of Y, meaning that Y is the generalization of X. So sheaf theoretically, you get a generalization map from the stock of X to the stock of Y in the M bar, and then dually, you get a morphism from M Y bar dual to MX bar dual, and that turns out to be a phase embedding. And the tropicalization of X, or rather, I mean, of this log space, is just defined by taking the co-limit over all these cones with respect to the phase embeddings. That looks infinite, but in reality, it's really finite because it only depends on the logarithmic strata, right? So these morphisms here, they're isomorphisms for most pairs X and Y, not most pairs, but they're isomorphisms for X and Y in the interior of the stratum, of the same stratum. So there are only finitely many strata, typically on a reasonable log space. And then this tropicalization is also finite, or at least it's locally finite. Okay, so that's a pretty harmless thing. It's a cone complex. And yeah, sometimes you can get some slightly funny self-intersections and so on. We assume that it's not happening. So think of this as a nice cone complex. And that map is factorial, or the tropicalization map. So whenever you homomorphism from X to Y, you get a map of cone complexes, trop X to trop Y. I should emphasize it's not only a cone complex. Each of these cones still have an integral structure. So you know what an integral point is, namely those homomorphisms that map mx bar to z, or to n rather, to the natural numbers. You know, so these are the integral points. And this obviously is a map that preserves this kind of integral structure on the tropicalization. So let's look at our two examples. The one was P2. And that's, well, let me spell it out, right? So P2 has one generic stratum. So away from the divisors, your log structure is trivial. Then you have these three divisors that gives three copies of n, and then three deepest points, so zero-dimensional toric strata, which have an n squared for the log structure m bar. Similarly for, I should have written r rather than n at each of these.
Divisor, right? That's P2 with its toric divisor.
Yeah.
As the log structure.
Yes. Sorry, I messed up here. Squared. So, and then what you get is they're attached in the way the fan of P2 is attached. But note that unlike the fan of P2, this is not embedded in any vector space. Okay, you should really think of these as three cones glued together, but they live abstractly. So even drawing this is maybe misleading, right? There are other ways to draw this. But this is, in any case, it's a support of the fan of P2. What we see from this immediately is the integral point.
So this is the U trop, right? This is like we've seen this U trop many times. Right?
Say it again. The what?
U trop.
U trop? What is U?
Like if U is the complement of the divisor.
Oh, I would argue that. No, that's not quite correct, I think. U trop is, I mean, it really takes a U, that's a GM squared, and the tropicalization of GM squared is really an R squared. Okay? This means, indeed, in toric cases, so if your space contains an algebraic torus, this induces an embedding of this guy into a vector space. Yeah, namely in the co-characters of this torus. And it's a characters or co-characters, whatever. It induces an embedding of this fan into R2. But what I'm drawing is really, it's not just R2, it's the union of three cones without any affine structure at this point. Let's put it this way, I would get the same tropicalization for any space, any surface, or any space actually, that just has three divisors meeting in this kind of configuration. They all have the same tropicalization. They look like this. Okay, it's pure combinatorial. It has nothing to do with the torus in the interior. Okay?
Okay.
So, but what we can see is that an integral point on the tropicalization has a meaning as an oscillation order of a family of points. What do I mean by this? Well, an integral point, this is given by a homomorphism from some mx dual, it's a map from mx to n. That's an integral point. So written this way, you see it has to do with a family from A1, from a map from A1 to your spec C of mx. Okay, and that gives you some kind of oscillation order, right? So if you think of this as being your toric model of your log structure, as I asked you in the definition, would always exist, then this tells you the order of oscillation of this family of points or curves, this oscillation of a curve, a one parameter family, to the divisors. So specifically, this would be the picture that I get when I write t maps to lambda 1 t cubed, lambda squared t squared, lambda 2 t squared. But the lambda 1, lambda 2 on this discrete level is arbitrary. You can't see it. Okay, but it's important to notice that the integral points have something to do with oscillation orders of families of points. So example B is already, so that was this two nodal curve, yeah? That was this guy. If you write it down if you try to write it down in this fashion, it gets a bit of a mess. And I'm not trying to do this. Actually, I also had a point here. And I rather observe that this is a relative situation. So it's not just an absolute tropical space, but it comes with the map to the tropicalization of Q. And I can understand the tropicalization of C0 by understanding the fibers of this pi for any point into the tropicalization of Q. So I view it as a two-dimensional family, pi inverse AB, and the dimensions, right? Tropical C0 will be three-dimensional. This guy is two-dimensional, so the fibers will be one-dimensional. And this is a family of one-dimensional rational polyhedral complexes, so not cones, right? Preimage of a map of cones is a polyhedron. And that's a length graph, just as a familiar tropicalization of a nodal curve. So let's go. So I claim that pi inverse AB is a following length graph. It has three vertices corresponding to these three irreducible components. And then it has two flat edges corresponding to these two nodes of lengths A and B, and then one leg of infinite length, which corresponds to the marked point. I don't have time to explain this very carefully, but let me just show you how a node gives you as a fiber and a finite, an interval like this one, or rather this one. So at a node, it looks like this. So I'm going to the standard log point. So recall that if I chose an integral point in this tropicalization, it gives me a one parameter family. So I can base change to the standard log point. This turns the base Q into a copy of n. And then I have a map to n squared, which is the log structure of a node over a standard log point. And this is just a diagonal map. One maps to 1, 1. Dualizing, you obtain the following map. You have this cone generated by 0, 1 and 1, 1, and you project it to the height, to the second coordinate. And now if you see, if you take the pre-image, so this is your pi. In this case, as a model case. And if you take the pre-image of A and this pi, you get this interval of length A. Okay? So this shows you that in this case, the tropicalization gives you a whole family of traditional tropical, abstract tropical curves. And that's a two-parameter family. It's a kind of the universal family of these kind of tropical objects. You know, that's the only parameters you can change here. So this is his interpretation for AB and n squared, right? So I said this already. Defines the base change, and what I'm writing down, the tropicalization is this pi inverse AB is the intersection of the tropicalization with the height 1. Or said differently, the tropicalization of the space change, which now is a curve over the standard log point, is a cone over this diagram. Maybe I should pause to give some occasion for questions. Have I lost everybody?
Perhaps. I can.
Okay.
So what can you explain what happened? What this last point again? So.
Okay, so let's look at here maybe, or is this one?
No, the first.
This one. Yeah. So let's look at a node over a stat log point. So the equation would really be something like ZW equals T. Yeah. So that's the map. So I map T to this guy. Well, it's just a family, the usual stable degeneration node, smoothing of a node. So the T would be the correspond to this n factor, right? The T comes from this. So the Cn, the way I wrote it here is the Cn is the Ct, and the C of n squared is generated by a polynomial ring over variables Z and W. So the map from CT to CZW, of course, maps T to ZW, which corresponds to this 1,1 element. So this explains this map. Okay. Now you dualize. Dualizing means exactly this kind of thing in appropriate coordinates. So this is a dual of the n squared, just written in a kind of geometrically appealing way. And that's the dual of n. And the dual of this map here is this guy. It's a projection to the second coordinate. Okay. And now you see that if I take the preimage of this point A, you get an interval of length A. Okay. Now, this situation is more complicated. We have two nodes. And what I gave you is a local picture on one node once we pull back to a standard log point. So we pull back to a standard log point by fixing A and B. So that gives the map from Q to N. Then I can pull back. I get a curve C0 prime over the standard log point. I tropicalize. And now I'm getting two pictures of this form, one with A and one with B. And that is exactly this picture. And then there's one more point, interesting point, which is this marked point. And if you do the computation, it turns out it becomes an unbounded leg. Okay.
Okay.
Okay, very slowly. I will have to speed up tomorrow. Maybe 5 more minutes, and then I have to stop. So, what I want you to get from this discussion on tropicalizations is that the tropicalization of X is really in 1-1 correspondence with M bar. So, if you know trop X, you know M bar, and the other way around. It's totally equivalent. So whatever statement I make about the tropicalization is really a statement about M bars. Okay, then I emphasize that the points of the tropicalization have something to do with contact data. The tropicalization is, of course, a complex of integral polyhedral cones. And then in the relative case, so if X is a log space over some log point, let's say, then the tropicalization is a family of rational polyhedra over the dual of Q. This is a cone, yeah, a rational polyhedral cone. Okay, so then let me at least say. Yep.
Just
yep.
Contact data?
Say it again.
What do you mean by contact data?
Like the one I said before here, this kind of thing. Yeah.
Like
so in particular, contact data of sorry?
All ways of making contact, all different quantitatively different ways of making contact with the. Yeah.
Typically of a curve at some point with the divisors that appear in the log structure. Okay, so let me say a few words on log grammar fitting invariants. Actually, maybe I should stop here. Time is over. I've talked an hour.
Maybe you can just very quickly tell us what it will be, so that we have.
So I guess I have to, if I continue in this speed, I will not really make it to canonical scattering diagrams. I don't know. Well, the log-gamma bit invariance, I define a moduli space. It's pretty obvious, right? I'll start tomorrow again with this, but it's pretty obvious. You just look at diagrams from a log curve to your log space over some log point. And then you can, of course, do this in a family. But a key question when doing this, if you do this, a moment of thought shows that this can't give a good moduli space. And the reason is simply that this Q is totally not unique. So, I mean, you can change it, right? So you could, for example, add a factor of n here without doing any harm. Okay, you can just keep on adding factors of n, and it has no chance to be a finite type moduli space. So the art of logarithmic moduli problem is to find some kind of good definition of your base monoid Q, this kind of basic log structure. So for stable curves, we have seen a good notion is you just put a factor of n for each node. But what is it for log-gamma Witten invariance? And the answer is, and that was really a key insight at some point in a discussion with Mark, where it's like, oh gosh, yes, I know the answer for a long time, and that's what I've looked for. I look at the tropical moduli space given by the tropicalization of this picture. Okay, so this gives you a family of maps from a length graph to this cone complex. And then I fix the kind of combinatorics. So I don't change slopes, I keep the strata and so on, but vary the length. And that gives you a certain cone. And the dual of this cone is your basic monoid. Okay, once you have this, everything goes smoothly. Okay, so then you have a nice moduli problem, you get a nice obstruction theory. I'll tell you how tropical geometry tells you about all the strata, everything you want to know about strata of your moduli space and these kind of things. Okay, so this will be what I'll tell you quickly tomorrow. And then I can come to punctured gamma Witten invariance, which will then be a small modification on the surface with some pretty interesting consequences in the details. But once I have the punctured invariance, it will be easy to write down these canonical scattering diagrams and so on, and theta functions you might have heard about last week already. Okay, so we'll stop here.
Yes.
Attention.
Any questions from the room? No questions from the room? Any questions from Zoom? If you have questions, you can just speak up. Okay, there are no. So I have a question. I still don't understand the mark point. Can you show us a little bit more about how the mark point changed the?
Yeah, let me, where was it? Here. Okay, let me just insert something here. Yeah, so let's just take one smooth curve, right? Let's just take a smooth curve. So that lives over a kind of trivial log point as at first, right? So let me write 0 to C. Okay, nothing interesting. But now, so it's just 0 everywhere, right? M bar is 0. Now I add a mark point. I don't change M bar here. I don't change the log structure on the base. The only thing I do is I coordinate Z here, or let me say something different. This was what I denoted capital Z, right? It's a divisor on the curve. So if we call this C, then I take MC comma Z. And that will be the new log structure. So obviously I haven't changed anything away from Z, but on Z, I added, because it's a divisor, is a vanishing order along this divisor. So the M bar becomes an N. And that's what's always happening. You're just adding the vanishing order along your mark point in the fiber direction. It doesn't change anything on the base.
Okay, I think I understand. Thank you. So there are no other questions. Let's thank Bernd again.